Welcome to another lecture of Analog Integrated Circuits Design. This is lecture number 3 in Unit 2, and here we'll be discussing about operational amplifiers. Just to quickly review what we have done in the other two lectures of this unit, we have looked at op-amp. We defined what an op-amp is. We have looked at the ideal characteristics, and specifically we saw what a single-ended and a fully differential op-amp is. Then we have looked upon a scenario where there is a need of a high gain amplifier with an accurate gain, and possible two options to implement that gain. And we realized that if you go for a closed loop implementation, keeping a very high open loop gain op amp as the core, the chances are that will give you an accurate gain compared to what you have as an open loop implementation, because of the variations what we have mentioned in terms of process voltage and temperature. Moving on, then we have taken one example and we saw what is the importance of having a very high open loop gain. So even though we need for practical closed loop applications, we may not need 1000 of 10,000 closed loop gain, but with 1000 or more than a high value open loop gain will definitely help in having a proper closed loop gain, and that we understood with this specific example, and we realized that there is a need for high gain op amps, and high gain op amps will definitely help in one aspect. What we discussed here is to have a gain with an error less than 1%. Then we listed out a few important parameters or the specifications of op-amp, and I also mentioned that in this class, in our AICD class, we'll be looking specifically at gain, ICMR, voltage swing, and to some extent we will also look at slew rate aspect. And then we listed the few op-amp topologies starting from one stage, two stage, and one gain boosting technique. And in the next class, we started telescopic op-amp. So to understand telescopic op-amp, again, we started from the differential amplifier that also can be called as a one stage op-amp. We know the gain of that structure, and if you remove the current mirror load connection, what you can see on the screen now, if you remove this, and if you bias this individually separately, you can definitely take differential output. That is a differential op-amp, what is seen on the right hand side. All right, but the gain remains same for both the structure. This we have analyzed before, and even for this structure, by applying half circuit analysis, we can say that the gain is equal to this value, gm of 1 comma 2 into r naught parallel to r naught. But the only difference in the fully differential version is your output swing will be doubled. That also we discussed the other day. Then we also like understood how to calculate the ICMR of a given structure, and we took the very simple example. So we know that op-amps are designed for having closed loop application, and one such important application is unity gain buffer, which is specially used for buffer applications. So in that, with that example, we saw how much can be your ICMR minus and ICMR plus. All right. In continuation, we also extended the structure of a single stage or a differential amplifier. The extension is possible by adding cascode devices, what we can see on the right hand side in the pink color. And with the addition of those devices, or by stacking additional transistors on the top of input as well as the original load, we extended the structure, and thereby we got a larger gain. And gain is derived by separately calculating GM and R out. And we also mentioned that the output swing in this case will be VDD minus the overdrive voltage of 5 transistors. All right. So this is what in brief what we have seen so far. And here I want to mention one more point, that you can see that the output swing here is 5 overdrive voltages we have to deduct from the supply voltage VDD. And if you are considering a supply voltage, a low supply voltage, say 1.8 or 1 or even lesser, you can see that few millivolt will be dedicated for the overdrive voltage. So you can seriously say, or you can say that your transistors or the transistors in the cascode will definitely consume some voltage headroom. or with that I can say one of the drawback of this structure. So see, it doesn't mean that when we mention something as drawback, that doesn't mean that the structure is not used forever. Any queries? I think one of you needs to mute. I don't know who is that. Abhishek, can you mute? All right.
Yes, sir. Good.
Oh, but I could see. Yeah, no issues. Fine. Yeah. So what we were discussing is one of the drawback. What I can say is there is a reduction in the voltage swing. Voltage swing is limited. That I'll mark as one of the drawback. Specifically, output voltage swing is limited because of a lot of cascode transistors. Moving on, in today's class, we will see one more drawback of telescopic op-amp. So again, I want to say that if we are listing drawback, the meaning is not that that structure or that architecture will not be used forever. We are understanding the positives and negatives of the structure so that we can use those structures wisely according to our need. That is the main intention of this. All right. So yeah. So before moving to discussing the drawback of telescopic op-amp, let us see how we can have a fully differential structure. So what you're seeing on screen now is the telescopic op-amp, which is single-ended. So now I'm going to convert this telescopic op-amp single-ended into fully differential. So I hope you guys will know definitely how you can convert this by removing this connection, these two connections here, and by biasing, say I'll mark this as VB3, and if I mark this as VB2, if I can bias this. So how will I bias? I need to use another circuit, a biasing circuitry separate. That could be that can be a current mirror itself. And if I remove those connections, I can see that we can take output from this point. What is the reason for that? The reason is whenever you go for differential output, the impedance seen at those points also should be same, and in this case that will be definitely same. So now you can take differential output from this, and this can be identified as a fully differential telescopic op-amp. Any doubt in the structure? I have just removed the connection. So this is fully differential telescopic op-amp. All right. Yeah. So now, so again, how will you identify the components or the devices here? It is same. This is your input differential pair. This is input differential pair. And these are the transistors which act as cascode for the input pair. Right. Now, these are the load devices, and these two are the cascode for the load which is connected. All right. So now, if you, let me ask you, what is the gain expression for this? So how can you write the gain expression for this particular structure? Gain remains same as that of the previous, the single-ended version, but more specifically, I can write it as minus GM of 1 or 2 into, yeah, let me check with one of you. Dhananjay Kumar, are you there?
Yes, sir.
Yeah, Dhananjay, can you help me in finding the gain of this structure?
Yes, sir.
Yeah, tell me what is the gain?
GM8,
All right.
RO8, RO4.
Yes, right. So how will I write that? So yeah, correct, Dhananjay. Thank you. I think you got the point. So since it is fully differential, it can be RO3 or 4. You can mute, no issues. RO3 or 4 parallel to RO2 or 1. So these are the initial resistances, but this will be improved by the transistors which can be GM7 or 8 into R0 of 7 or 8 on the upper side, and here it is GM of 5 comma 6 into R0 or 5 comma 6 on the lower side. So this is how you can represent the voltage gain expression for this fully differential structure. Now in a similar way, if you write the output swing also can be written here. Only one difference what you will notice is output swing also will be same as the previous case, but it will be just twice of that, because we are measuring not with respect to ground or with reference, rather we are measuring from two differential points. So we can write the output swing as twice of that of previous. The previous is VDD minus the overdrive voltage. I hope I have used this notation as overdrive, VOD. Yes, it is VOD or VOV. Yeah. So VOV, overdrive of 4. I'm just writing for one side, but it could be for, it can be for the transistors 3, 4 minus transistors 7, 8 minus VOV of 5, 6 and minus VOV of 1, 2 minus the overdrive of the transistor 0. So I'll write it as 0. So you'll be wondering which is transistor 0. This is 1, 2. This is 0, and this need to be replaced by a transistor itself here. And that will be biased separately. Maybe I'll mark this as VB0, and this is the structure of a fully differential telescopic op-amp. All right. So I hope this is clear. We haven't done anything new. Rather, we have just replicated the equation, same equation with proper numbering, and output swing is double that of the previous. Now, let me quickly go and discuss another drawback, what I was mentioned. So let me write this as drawback 2. The first drawback is the limited output voltage swing. Yeah. So, so another drawback of this cascaded cascoded op-amp or a telescopic op-amp of this type is, we know that, or as we saw before, there are many open closed loop applications for op-amp, and one such closed loop application is to use it as a buffer, unity gain buffer. So when I say as a unity gain buffer, this is what exactly meant. So plus here we'll be providing the input voltage, and to the minus output will be short to the negative input terminal or the inverting terminal by giving full negative feedback. All right, so what I have done here is I have just shorted output back to one of the inputs. So what I have done here is I have shorted or I have connected shorted V in and V out together. So when I say V in, only the negative input terminal is connected. So can I know, are you guys with me? Can I get some response in the chat? If you are listening, please write yes. If you're not able to listen, you can write no. Okay. Just want to know how many are responding. Yeah, around 12, 13. All right. Yeah, thank you for that. So what we are going to discuss is the second drawback of telescopic op-amp, and let me list the drawback first. Let me write the drawback first. Okay, before writing the drawback, we'll see the scenario. So what we do is we are just using this cascoded op-amp, which is the telescopic op-amp, as a unity gain buffer. We'll see how this cascoded op-amp will act as a unity gain buffer, and then later talk about the difficulty or drawback of that. All right. So what we are going to do is we are looking how a telescopic op-amp can be utilized as a unity gain buffer. All right. So for that, let me again bring this structure here. All right. So Yeah, what you can see here is single ended. So if you look at this diagram, the block level representation, what I need is a single ended op amp. So I'm just removing all these labels from here, and I need to connect the output. So output is here, this is the output point V out, and output need to be connected back to this terminal, where this being the plus and this being the minus inputs of the op amp. So I need to do a connection of this. So in block level, what you're seeing on the left hand side, what I'm highlighting now, what you're seeing here now, on the left hand side is a block level, and the same thing, I just placed the circuit diagram on the right hand side. I hope you can see that here. This is the circuit diagram, and now at the output I just connected, or I shorted output back to the negative input. That is what you are seeing now. All right. Now we know for sure that in amplifier, or for any circuit, as to work as an amplifier, especially MOSFET based circuit, we need to ensure that transistors should remain in saturation. Then only we will get a high output resistance, and it will act as a constant current source. That is the idea behind amplification. So now when I do this shorting, when I connect output back to input, we are also connecting the see, when I do this connection from the output to the negative input here, what I'm doing is I'm connecting the output common mode level to the input of transistor M2, or in short, I should ensure that the transistors M2 and transistors M6, all others will be definitely in saturation, but by this connection, transistors M2 and M6 also should not go out of saturation, or I should verify whether transistors M2 and M6 are in saturation or not. Are you getting the point? Are you getting the point what I'm telling now? Since I am making this connection from output back to one of the input, I also should verify how the transistors are getting affected by shorting output to input. We just like that we cannot short. By connecting output to input, what is actually happening is even the DC level at that output point is also set same as that of the negative input terminal of the op amp. So now I need to verify whether the transistors M2 and M6, whether it will get affected or not, or we should ensure the saturation condition for the transistors M2, M4 and all the other transistors in the circuit. And also now this is the point where you will get the output voltage. So now if I'm providing an input signal here, what I'm expecting is the same signal at this point, right? Now by this shorting, whether is there any difficulty at the output swing, or by shorting this output back to one of the negative input terminal, whether the transistor or whether the circuit can support a support some output swing is what we are going to study now. Am I making some sense in my statements? Are you guys with me?
Yes, sir.
All right. Yeah. Thank you. Others can also respond so that I'll know that you are just following what I'm telling. All right. So my first job is to see whether the transistors M2 or M6 are maintaining the saturation condition, or we should enforce that condition now. So let me check for M2. So for the transistor M2 to be in saturation, what do you think? What is the condition what I need to be maintained? So let me just name this node as, so there is a node here. I'll use a different color, and I'm just making this node I'm naming as Vx. This is named as Vx. Now this node, yeah, anyway, this is the output node. I'm just marking it as V out. All right. Now this is, I'm just leaving it as VB. Very good, Sri Harsha. Yeah, so you have written the condition for saturation for M2 is VD should be greater than VG minus VT. So in this case, if I write for M2, the VD for M2 is actually Vx, right? The VD for M2 device is Vx, so Vx should be greater than, what is VG? For M2, the VG is same as V out, so Vx should be greater than V out minus Vt. That is my first equation, what I can write with respect to device M2. All right, so Vx should be greater than V out minus Vt, or if I write in terms of V out, I can also say that V out should be less than Vx plus Vt. That is my first condition. All right, now what is Vx? How can I write what Vx is? So Vx is the DC potential in the circuit. So how will I write Vx? So Vx can be written immediately with the help of this Vb voltage. What is Vb? Vb is the voltage coming at the gate of M6. Now from that, Vb voltage, if I reduce one VGS, that is the VGS of 6, I can say that is a Vx voltage. So I can write Vx equal to Vb minus VGS of 6. All right. So if you have any problem in the colors what I'm using, if it is not clear to you guys, please do let me know. I'll just change the color. So Vx is equal to Vb minus VGS6. How will I know Vx is that value? Vx is directly from Vb and one VGS lesser than Vb. So Vx should be equal to that. Now, so if that is the case, I can write Vout should be less than Vb minus VGS of 6 plus Vt. Or if I write it little more proper, I can write it should be equal to Vb minus, I'll take this into bracket. So this is Vb minus VGS6 minus Vt. So to ensure the saturation condition for M2, the output node voltage should be less than Vb minus 1 overdrive. It is equal to 1 overdrive. What you have is VGS6 minus Vt. I'm just keeping this condition at one point, right? Similarly, now if you will be wondering why I have written the condition for saturation in terms of Vout. The reason is this. So how will I write the saturation condition for M6? Now for M6 in saturation, what is the condition? Again, the condition remains same as what Sriharsha has written in the chat. The VD should be greater than VG minus VT. What is the VD of this M6 device? It is Vout. Yes, Vout should be greater than VG is nothing but VB minus VT. That is a condition. Vout should be greater than VB minus VT. Now, why I have just changed the condition for saturation of M2 in terms of Vout is just to have a comparison for both the transistors in the just to bring it on the similar lines. All right. So now I can say, in order to ensure the saturation condition of both M2 and M6, I have two conditions. One is my Vout should be less than Vb minus VGS6, Vb minus VGS6 minus Vt. That is my first condition. And my second condition is Vout should be greater than Vb minus Vt. What is the meaning of this? The meaning is in order to ensure the saturation condition for M2 and M6, your Vout should be within this range. How will I understand about this range? Let me talk about this range a little more here. Say this is your Vb voltage, and let me mark this point as Vb minus Vt. Now your output voltage should be greater than Vb minus Vt, maybe the bottom level. This is Vb minus Vt. And at the top level of the output should be lesser than 1 overdrive to Vb. So if I am marking this as some VGS6 minus Vt, which is 1 overdrive, then this level is, so this level which I am marking in this color, what I have marked here, that line will be Vb minus 1 overdrive. So what is the meaning of this? So if you look at this entire range, what I have is one threshold, right? The top line is Vb and the bottom line is Vb minus Vt. So the gap is only one threshold, and within that one threshold, one overdrive is taken away, and whatever is remaining is actually available for the output voltage to swing. All right. So what is the implication here? Now you are allowed, or in the circuit, I can have an allowable range. So this is actually the allowed range of the output voltage to swing. And only within this range, if we make the output voltage to swing, the transistors M2 and M6 will remain in saturation. All right. I think this is clearly, this can be clearly seen that the output voltage swing is very, very less. All right. It is lesser than 1 overdrive, or it is as small as 1 overdrive minus, lesser than 1 threshold, and it is lesser than 1 threshold minus 1 overdrive. All right. So the second difficulty here is, if you are using cascoded op amp like telescopic op amp as a unity gain buffer, it cannot be utilized as unity gain buffer because there is difficulty in shorting the input and output. So what is the difficulty? If you do that, the output swing available is very less. So that is a difficulty in shorting output and input. I hope this is clear what I have done here. So the concluding statement for this discussion is, I will write it here as cascoded op-amps are not used as or rarely used as unity gain buffers. So again, the intention is not to say that cascoded op-amps or this telescopic op-amp is useless. That is not the intention. The intention is we cannot use it for buffers for the reason the output swing available is very less. So is this clear what I have discussed so far? Any questions? All right, so you may need some time again to think and understand this. So if you have questions further, please put in the chat box. Yeah, Shrihash, I saw the other condition what we have written also. All right. So with this idea of the structure of single-ended, the structure of fully differential, and with the help of understanding the drawbacks of telescopic op-amp, let us now focus and let us now see how we can design a fully differential op-amp. So let us start discussion on the design fully differential op-amp. Let me write it as telescopic op-amp. All right. So let me just list the specifications here. The specs given for the design are this. One is supply voltage, which is given as 3 volt. Another one is differential output swing, which is also given as 3 volt. Another spec given is power dissipation, that can be less than or equal to 10 milli. The maximum power you can dissipate is less than 10 milliwatt. Yeah, Avinash, I saw your question. Yes. Yeah, the first drawback says that yes, when you use it as an open loop configuration, you need to your output swing is just five overdrives. You have to reduce 5 overdrive voltage from your supply voltage. That is that only that much you will get as the output swing. And the second one is again in a closed loop, specifically in a unity gain buffer mode. There also the output swing is limited. Yes. So with that I can say yes, both the drawbacks are pointing towards the low swing. Nevertheless, yeah, but the point here is when you say the output swing is less, the other advantage of this is it will definitely give you a huge gain. So we have to look for applications where your swing is not a much concern, or there are many methods or techniques to overcome this. So now telescopic op-amp as a standalone circuit, yes, the output swing is limited, but in order to have a larger swing, the general technique or what we use is we will go for two-stage op-amps. The first stage will be your telescopic op-amp, which will contribute a lot of gain, and we'll have a second stage where we will use minimum transistors on the stack, so that that stage will contribute for a larger swing. So there are various techniques to avoid this. But as a standalone circuit, yes, telescopic op-amp will give you a restriction on the output swing. Is that clear, Avinash? All right. Thank you, Avinash. All right. So now the specifications are written here. There are four main specifications given. The supply voltage is 3, differential swing is 3, power dissipation is less than 10 milli, and the voltage gain requirement is close to 2000. All right. Now I'll also write the other constants what we use for this. Let me write it here. The mu and Cox value, which is 60 microamps per volt square. Similarly, mu P Cox is little more lesser than that, which is 30 microamps per volt square. Then lambda n, which is a channel length modulation parameter for NMOS device is 0.1, and for PMOS device is 0.2. And for the time being, you can think of gamma, the body effect parameter, equal to 0, and the threshold VTN and VTP both equal to 0.7. VTP is minus 0.7, so the mode value can be assumed as 0.7. And these lambda values are actually given for lambda is always related to the channel length, and this is for the minimum channel length of 180 nanometer. Sorry for writing in this way, because I thought I'll start design in this page itself. All right, so the lambda value, the channeling modulation parameters are defined for the length of the channel. That is why I have just mentioned that lambda values are defined for L minimum of 180 nanometer. That means, sorry, not 180, we'll go with 500 nanometer. So that means when you increase the length of the MOSFET, lambda values also will have an impact on that. All right. So since the question is to design a fully differential op-amp, we will take the structure of the fully differential op-amp itself and we'll proceed with that. All right. So this is the architecture, right? So so what we basically do is when we say design, as you all know, we will be focusing on, we'll be trying to find the aspect ratio of the transistors. Aspect ratio is nothing but W by L. But apart from that, the general idea is when you are going to design a structure, design a circuit. Say for example, in this case, it is a telescopic op-amp. We'll be designing the value of W by L. With that, we'll have the GM value, we'll have the R naught value, then W by L, then we'll calculate the gain of the circuit. So all those things will be discussed in this particular design. All right, okay. So let us start with the design part. So we'll do this design in steps. So the very first step is, if you remember, when we have discussed about the differential amplifier design, the very first step is to find the current through all devices. Let me just write it over here again. We know that the drain current what we are assuming in saturation is the mu and Cox, half mu and Cox W by L into VGS minus VT the whole square for NMOS device. So the idea is, if you want to design W by L, we should know what is ID, we should know what is VGS minus VT. These are the two steps what we do. So in order to get current and in order to get the overdrive voltage, we will start either from the slew rate specification or from the power dissipation specification, whichever is given. So in this case, we will see how we can start from the slew rate specification. All right. So, okay, let it be there. Yeah, so the first step in the design is we generally call this as power budget allocation, or I'll write it as finding the current, find currents find the current through all the transistors. That is the first step. So we'll do step by step. This involves certain calculations, so please keep your calculators ready with you. All right, so this is the first step. Now, how will you find the current through all the transistors? As I mentioned, we may go for power dissipation spec here. So the power dissipation given is equal to, power dissipation is equal to the supply voltage VDD into the total current in the circuit. You can think of total current as a current flowing through this M0 device, which is equal to, you can mark it as ISS, and that VDD into ISS is given as the total power what we can utilize should be less than 10 milliwatt. In that case, given VDD, you can find what is ISS, and the maximum current what you can use in the circuit is 3.33 milliamps. That is the maximum current what you can use directly from the calculation. So ISS max is equal to 3.33 milliamps. So now a designer should thoughtfully allocate the current through different branches and make sure that the total current should not exceed that of the 10 milliwatt power. So even though ISS max is 3.33, generally we will not go with that maximum current, because we may need some current even for the biasing circuits to, so some part, maybe 1/10 or some portion of current from the main branch need to be again circulated through the biasing part. So we will not take the entire 3.33 milliampere as the ISS current, rather we will allocate ISS current of say some 3 milliamps. Now from here on, you'll be wondering when you do design. So you now, if your question is, can I consider ISS as 2 milliamps? Yes, definitely you can go ahead and design for 2 milliamps, provided you are satisfying all the other specifications. So you should satisfy. So if you go for a current of 2 milliamps, definitely power dissipation spec will be satisfied. But you should also see whether the gain is satisfied. You should also see the output swing will be satisfied or not. So that is the only condition. All right. So as of now, I'll fix the current as 3 milliamps. Now, if the total current is 3 milliamps, if ISS is 3 milliamp, I can say that there are two branches here, two cascode branches. Each will be carrying a current of ISS by 2, and what I'm writing as current here is nothing but the DC current. All right. So what can I write here additional? So now current in each cascode branch, there are two cascode branches. So current in each cascode branch is equal to 1.5 milliamps. So that means transistors from 1 to 8 will carry 1.5 milliamps of current, and transistor 0 will carry 3 milliamps of current. So with this, we got the current flowing through all the devices ID. All right. And from where we have obtained the current, we have taken current calculations or the current value directly from the power dissipation spec. Now, what should be the next idea? What should be the next step? The step 2 should be to find the overdrive voltage for the transistors. So there I'll go for step 2. So your step 2 is to find the overdrive voltage VOV or VOV for all the transistors. With those two, we can directly find the W by L value, right? So that is why the step 2 is to find the overdrive voltage of all the transistors, and to make sure that the transistors overdrive will not is such that you will have the required specific output voltage swing. We will derive this output overdrive voltage for the transistors from the differential output swing spec. So it is given that differential output swing will be equal to 3 volt. So what is the meaning of that? So looking back to the circuit, when you measure the output voltage between these 2 points, say plus minus like this, the voltage swing across these 2 points will be equal to 3. That means each node, this node here and this node here, both should have a swing of at least 1.5. So here if it is going to 1.5 and on the other side if it is going to minus 1.5, altogether I can say the peak to peak swing across the output terminals will be equal to 3 differential swing. All right. So with that understanding, I will write each output node of the Cascode branch, each output node of the Cascode branch should have 1.5 volt as the swing. So each node should have 1.5 volt swing. In together as differential, you will have 3 voltage of output voltage swing. Is that clear? Any questions on that? Any questions on that? So for better understanding, you can think of like this. This is the 0 volt point and this is the 3 volt point. And say somewhere here is your output DC. We do not know what is output DC, but we know that you have an output swing of this much. And I'm just drawing on one side, only one side I'm writing. So this should be equal to 1.5. Similarly, you have one more branch on the other side. On the other side also you will have 1.5. So differentially you will get 3. All right. So what is the takeaway from this? If you are allocating 1.5 volt the output voltage to swing, the rest of the 1.5 can be utilized for the transistors in the stack. Meaning, VDD minus 1.5 volt, that is equal to 3 minus 1.5, which is again equal to another 1.5 volt, and this 1.5 volt is available for the transistors in each Cascode branch. So in each Cascode branch, we know that there are 5 transistors. So from this 1.5, we can allocate to all the transistors in the swing. All right. So we'll be continuing this in the next class because we'll not be able to finish the design part in another 15 minutes. So we'll be continuing in the next class, and I'm just winding up classes now. If you have any questions, you can ask.